Herhalde sesim duyuluyor değil mi?
Evet hocam.
Tamam. 102 nolu sınıfta anlatıyorum. Hani gelmek isteyen olursa da gelebilir, onu da söyleyeyim de. Şimdi size şeyleri gönderdim herhalde değil mi? Syllabus'tır, kitap vesaire göndermiştim. Eğer ulaşmayan varsa bana söylesin, tekrar göndereyim. So in this course, what are we going to do? We are going to study differential equations, more specifically solutions of ordinary linear equations with a singularity which is regular at a point. In the differential equation course, Math 254, you have seen those kind of equations. So there are equations like this: x squared y double prime plus 3xy prime, let's say 5y equals e to the power x, for example, something like this. Or I don't know whether this was 0 or not. Okay. So solutions of this power series solutions of this, if you look for solutions of this kind, probably you will not get a solution, okay, of this kind. The solution of this equation is more complicated, and in the differential equation course, usually we just write down the form of the solution, and then we don't talk about how you derive that solution, and we actually just do examples where you find one of the solutions. Since this is a second order equation, you expect two linearly independent solutions. Obtaining one of them is not that difficult, but the other one is more complicated usually. And usually in that course we ask, find one of the solutions corresponding to the larger root and so on. In this course, what are we going to do? Using topology, we will understand the nature of these differential equations and how you obtain the solutions. We will see that actually, if you use topology, everything becomes much more clear and understandable because the form of the solution of this equation is rather complicated. I don't remember now, but it's something like this. There are some logarithm terms, and then some functions times logarithms and so on, and then some power series. I don't quite remember, but form of the solution is quite difficult. And if you look at the book doesn't have even one solved example in the book, okay, because it is complicated, and the author just didn't care much, probably because you may write down a method and a solution, but understanding the method is not easy, so they just mentioned how the solution looks like and then leave it there. We will study those differential equations using basically geometry, actually a more relaxed form of geometry, which we call topology. So first, let me just write down maybe the title of the course. So MET 424, Galois theory of covering spaces, and linear differential equations. You probably heard Galois theory in algebra courses. We have actually an elective course called Galois theory. It is related to field extensions. Basically, if you have a field extension, what we mean by field extension, you have a field, and let's say this is a subfield of a bigger field. You may consider E as a vector space over F, and then it has a basis. In case it is a finite dimensional vector space, then you may write down a basis and so on. And then you consider automorphisms of this field extension, automorphisms of E, but F linear automorphisms, okay? Since you may consider F as a vector space over F, you may consider linear automorphisms of E over the field F, and then this forms a group. And it turns out that there is a nice relation between this group and this extension. This is discovered by basically Galois. What he did is the following. You have this field E, F and E here, and then in between those, there are lots of fields. Let's say E1, and then E2, and then, something like this. Complicated diagram. So these are kind of intermediate fields. This is the smallest one, this is the biggest one, and there are some intermediate fields. In case this extension is a special one, which we call Galois extension, then there is the following picture. So this picture of field extensions and subgroups of this group, automorphisms. So you have this G here and subgroups of this. One subgroup is just the identity element, but there are, of course, lots of intermediate subgroups. And what we know from Galois theory is that there is a one-to-one correspondence between the subgroups and subfields. And properties of the subfields are reflected to the properties of subgroups. For example, when a subgroup is normal, that is a corresponding property in case of subfields, okay? This is known as Galois theory, and using this theory, we can say a lot of things about fields, and we can talk about solutions of algebraic equations and so on. For example, you can do the following. Here you have, let's say, this field, and you add this field square root 2 and square root of 5, okay? So this is your E, and then your F is just Q, and then there are subfields. For example, there is Q of square root of 2. You just add square root of 2 inside Q, okay? So what we mean by that, Q, when you add something like this, if you add an, let's say, complex number which is not rational, we mean the following. Polynomial expressions of R. So PR divided by QR, where PX and QX are polynomials. Okay? So, for example, R squared plus 1 divided by 3R minus 5 and so on. Okay? So this becomes a field itself. And we have these subfields, Q5, and maybe some other fields. And you get a diagram like this. I am not 100% sure what I'm going to say may not be correct, but for this, for example, field extension, probably the Galois group, G is şimdi atıyorum bu kısmı da. It is either Z2 cross Z2 or Z4. I'm not sure which one. Efendim? Evet. Neyse %100 emin değilim ama. Neyse böyle bir şey. Tamam mı? Bu yapılabilir. So we have such a correspondence between subfields and subgroups of automorphism group. What about topology part of this? This picture has a topological counterpart. So that's what we call Galois theory of covering spaces. We will define what's a covering space, and we will see that the same theory works in case of covering spaces. We have covering spaces and automorphism groups of those covering spaces, which we call them deck transformation groups. And then we have almost the same diagrams. On one side, we have deck transformation group and its subgroups. On the other side, we have covering space and intermediate covering spaces. So instead of fields, field extensions, we have extensions of topological spaces. Okay. Therefore, this Galois theory has a geometric counterpart, and there are actually more relations between this geometry and algebra. We will not go into details of those, but everything we do in algebra can be translated actually into topology and geometry. Okay. So, and one advantage of this will be, this theory can be used to understand solutions of ordinary linear ordinary differential equations with a singularity which is a regular singularity around a point. Okay, and at the end of the course, we will fully understand what's going on. Okay, and that theory is something actually studied just after Galois theory was born. People said, okay, now we understand how to solve algebraic equations using Galois theory. What about differential equations, right? They are also equations. And Sophus Lee was one of the pioneers of this theory. He couldn't do what he wanted to do, but Meanwhile, he developed the theory of Lie groups and everything. Okay, so it's a huge theory, very nice theory. So as a byproduct of his actually studies, we have now the theory of Lie groups and so on. But later, people actually made substantial advances, I mean, developments in the theory. And this theory is something today studied also. It's a, active research area. And it contains differential equations, algebraic geometry, group theory, fields, and everything. Okay, it's a very rich area of research. I don't know much about those theories, frankly. I don't study, but this course will give you some idea. Meanwhile, you will understand several things about covering spaces, Galois theory, and so on. Okay. So this is what we are going to do, basically. Now, about covering spaces, let me give you a couple examples. Covering space means you have a topological space downstairs, and then you have another space above it, and then you have a map between them. That map is always a local homeomorphism. Okay, this means that if you are on the space here or above, you don't realize at which space you are in, because they are locally the same. If you don't see the whole space, then you will think that you are in the same space, but actually you are somewhere else. One example, for example, consider this circle, and then another circle here. Suppose that they are both unit circles in the complex plane. Okay, so this is the unit circle in the complex plane, meaning that complex numbers, so that this has norm 1. And the map is the following. You take a complex number and send it, let's say, z to the power n. Let's say z cubed. Okay, so your map is this: sending circle to circle. One-dimensional sphere is circle, and we denote it like this, and it sends z to the power n. So in this case, z cubed. And how this map behaves, you see, this map sends any unit complex number is written like this: e to the power I theta, and p of this, cube of this number, is of course e to the power 3 I theta. So what it does, it just multiplies the angle of that complex number by 3. So if this is, let's say, no, I measure from here. If this is theta, then this is 3 theta. Of course, modulo 2 pi, okay? Because when you go 2 pi, if you add 2 pi, you are at the same place. So it is this map. And if you are, for example, at a point here, let's say this point, then in the preimage of this, you have 3 points, because this is the map z goes to z cubed. So every number, complex number, has 3 square roots. So there are 3 numbers which are mapped to this one. One of them is this, let's say. Let me call it Z1. And then two other ones, we know that they are equally spaced, right? So Z2 and Z3. And what we mean, so these three numbers, which are equally spaced, so these angles are all 120 degrees. They are both mapped to this point. What we mean by a local homeomorphism is the following. This map, of course, is not a homeomorphism because it is not even one-to-one, right? It maps 3 points to 1 point. It's a 3-to-1 map, okay? 3-to-1 map because, you know, every complex number has 3 cube roots unless it is 0. And 0 is not here, so every point here has exactly 3 images. And this is a local homeomorphism, means the following. If you have a small neighborhood of this point, that neighborhood has 3 pre-images here. And when you restrict your map to these pre-images, it's a homeomorphism, okay? So P restrict to this set, and this set has this image, and they're all homeomorphisms. So if I call this V, let's say this is U1, U2, and U3. So this map P from UI into V is a homeomorphism. Okay. This is an example of a covering space, for example. Okay. Another example of covering space can be obtained from this figure. From this covering space, for example, you can do the following.
Sir, would it be possible for you to define covering space as well, or will you do that after
No,
the examples?
I'll do that. Yeah, but this is just motivation. I'll describe all those carefully. Don't worry.
All right, sure, because I got a little confused with covering space.
Yeah, I didn't define what's the covering space yet, but I'll do that. Okay. I'm just trying to give some idea what kind of objects they are, but we will define them very carefully. Okay, now we have this covering space. Let's say Z goes to Z cubed from S1 to S1. What you can do is the following. Just attach a circle like this, okay? Which we will call this gadget S1 wedge S1. I'll also define this gadget. It means this is just a junction of two spaces at a point. We call it wedge sum or wedge of two topological spaces. What happens is the following. This point had 3 pre-images like this. Okay. And what happens is that you have just this circle attached to all these points. Okay. So pre-image of this circle will be just this gadget. And this is also an example of a covering spaces. This is much more interesting compared to that one. The one without these small circles will correspond to the cyclic group Z3. Okay, the deck transformation group will be Z3. But for this one, yeah, okay, it's also Z3. Yeah, the map is the same. Okay, so it will be again Z3. Here, our map is like this. So For example, if you are at a point here, then this has 3 images like this, pre-images. And your map restricted to these are homeomorphisms. However, if you are, let's say, at the point here, then a neighborhood of this, will be a piece like this plus another piece like this. So pre-image of this neighborhood will be a part of this circle and a part of this circle. So it will be, something different. But again, it's a local homeomorphism, okay? If you are here, what you see is this purple arcs. And if you are here, you see the same picture. So locally, they are the same. But globally, of course, they are quite different objects. Here we have only 2 circles, but here we have 4 circles. Okay? But locally, they are the same. So these are some typical examples of covering spaces. We will see a lot more examples, but we will go slowly. First, I will define what's a topological space, what's the homeomorphism, and so on, what's the topology, and so on. Yes. Local homeomorphism means the following. If you are at this point, and suppose you are nearsighted, you don't see the whole space. You just see your neighborhood. So if you are at this point, your neighborhood is like this. You have one path like this, another path like this. What I'm claiming is that if you are at this point, then you see the same picture. Okay, so locally, these are the same spaces. This P is a homeomorphism, okay, locally. But globally, they are different objects. So such things are called covering spaces. So a covering space is basically a onto map from a topological space to another one, which is a local homeomorphism at each point. What we mean by a local homeomorphism, you have a neighborhood of your point, and then image point has a neighborhood downstairs, and your map is a homeomorphism from this neighborhood to this neighborhood. Okay? We will define all this carefully, so don't worry about that. Z3 ile bağlantısı işte şuradan geliyor. Z küpten. Every point has 3 images. Okay? So that's the, but this is an easy kind of simple covering space. The deck transformation group is cyclic group Z3. You can get almost any group you want as a deck transformation group here. Okay, so you can get, for example, Sn or I mean products of these gadgets and so on. Okay, or almost any group. And what happens is that using this theory also, you can prove results in group theory, which are usually a lot more difficult to prove if you are just using elements of algebra. Okay. For example, you can prove the following. The free group F2 contains free group on any, so F5 or F, and any of these groups sits inside, and the index in this case, index is what? Index, let's say K as a subgroup, and that K is just 1 minus N F1 minus 2. Okay, so if Fn is a subgroup of F2, then the index should be this number. Using topology and covering spaces, this is easy to prove. But if you don't use it, it's not easy. Okay. There are, of course, algebraic proofs, but they are not easy. Okay. Bunları mı yapabilirsin? Yani hatta şunu da yapabilirsin. Onu söyleyeceğim. If the cardinalities of two sets are the same, you can always make them homomorphic by changing the topology. Suppose f x and y has the same cardinality. It means that there's a bijection, right? So this is a bijection. If one of them has a topology, using that bijection, you just carry that topology over here, then they become homomorphic. So topologically, set-wise, all of us are the same, right? Anything in the tree space, any set which contains an open ball has uncountably many points. So this interval has uncountably many points. R has uncountably many points. Rn has uncountably many points. And you can write down bijections. It won't be easy, but you can do that. And then you can just carry this topology here or here. They become all homomorphic. So topologically, we are all the same, okay? I mean, not... so what I mean, just we are set-wise the same. We have all uncountably many points. What makes us different is the topology on that set. Okay, one of them becomes Ahmet, the other one becomes Ayşe. But so set-wise, they are the same. Set-wise, we are all the intervals 0, 1. Okay. So let me just start by defining what is topology and so on. Okay. A topology.
Hocam kamerayı çevirir misiniz?
Evet, tamam. A topology on a set X is a collection let's call it tau of subsets of X satisfying the following axioms. What are those axioms? As subsets, the empty set and the X itself should belong to this collection, okay? Both empty set and X. So the smallest and the largest subsets are elements of this topology. The second one, if you have finitely many elements in tau, then şöyle yapıyorum. Then their intersection also belongs to this collection. Okay, this is the second axiom. And the third one is the following. If you have a collection of open sets, let's say U alphas in this tau collection, and this index set could be anything. It can be a finite set, an infinite set, countable set, or any other set. So this is an index set. Then the union of all these should also belong to this collection. So this means what? This collection should contain empty set and the whole space. It should contain finite intersection. Sorry, it should be closed under finite intersections, meaning that if you have finitely many elements, then their intersection lies there. And it should be closed under arbitrary unions. Okay, so such a collection is called a topology on X. We have seen, examples of topological spaces in calculus courses and analysis courses. Elements of tau in a topological space What is the topological space? The set with this collection, okay? So this pair is a topological space, and elements of this collection are called open subsets of the topology. Okay. So open subsets are the elements of this collection. Closed subsets, what are they? They are just complements of open subsets. A subset C of X will be closed, will be called closed if X minus C is open. Okay. I guess you are familiar with these concepts, right? But here, unlike metric spaces, we don't need a metric, okay? In metric spaces, you have a tool to measure the distance between points. In a topological space, the distance between the points is not important. We don't care about that, okay? Okay, I'll define some more stuff related to topological spaces. A subset, let X be A be any subset, be any subset. The closure of A denoted as A bar is the subset defined by it's the intersection of all sets such that those sets contain F, A, and F is closed. So closure of a set is just the intersection of all closed sets containing A. Since arbitrary unions of open sets is open, arbitrary intersections of closed sets is closed. Therefore, this set is always closed. Okay, which is always closed. I am, defining all these things a bit, I move a little bit fast since you are familiar with these concepts, but if there's anything you don't understand, just let me know. Okay. Okay. Yeah. Similarly, the interior of a subset A denoted as int A or like this is the open set defined by so this time you take union of all subsets which are contained in A, but you ask U to be open. Okay. And this is an open set because it's a union of open sets. If it's a union of open sets, no matter what they are, it's always open. Okay, let's see some examples. Finite topologies. Suppose, for example, X has just 3 elements. Okay. Of course, tau1, which is just the power set. Okay, I can denote it like this or like this, power set. The set of all subsets of this set is, of course, a topology, is a topology on X. It is the biggest topology because you take all the subsets, but there are more interesting subsets, I mean topologies. For example, we may consider this one, empty set. We know that this two has to be in the topology, empty set and the set itself. And then you may have some other stuff, let's say A, B, and just this. Okay, this is another topology on X. So both of them are topologies. It is clear that this set is closed under unions and intersections, right? This collection. The study of topologies on a finite set is not something actually finished. There are still works on this. Actually, one of our graduates, Yasir, has a publication on this subject. Topologies on finite sets. So how many topologies one may have on a finite set and so on. Okay, it's not something fully understood. Okay, another. So this is one example of or two examples of finite topologies, but there are of course more. Let's take any set. The smallest topology on X is the topology consisting of empty set and X itself, right? This is a topology. It's of course a trivial topology. It has only two open sets, the empty set and X itself. So it is not interesting. This is also called the weakest or coarsest topology on X. Yani it's also called weakest topology because it has only just two open sets, or we call it coarsest topology, meaning that it's very so in Turkish we say kaba topology because it has only two open sets. And we have the opposite of this. On the other hand, I'll finish in a minute. The topology, tau, which is 2 to the power x or px, the set of all subsets is the largest topology. on X. It's also called the strongest or the finest topology. This is also trivial in the sense that, you know, every subset is open. But we call it stronger or largest because it contains all other topologies, because you have all the open subsets, okay? Not just a few of them, but all of them. That's why we call it the strongest topology. All right, so I guess we may stop. Sorusu olan var mı? Ben kayıt aldım inşallah. Tamam.